So the first part of covalent bonding is on electronegativity, basically a recap of what we have learned previously. Alright? So recall that electronegativity previously we defined it as a measure of the tendency of an atom to attract a bond pair towards itself. Can you still remember? Another thing that you have to recall is the trend in electronegativity. So I already emphasized that electronegativity increases across the period and up the group, which means it increases diagonally from the bottom left to the top right hand side. So this is the second thing that you have to know. And previously we talked about electronegativity difference as well in ionic bonding, and I showed you this diagram over here. Can you still remember? Yes, right. So I mentioned that for those bonds with electronegativity difference of less than 0.4, they will be classified as covalent non-polar, and those that's higher than 0.4 and lower than 1.8 is considered covalent polar, whereas those that's above 1.8 will be ionic. So this chapter will be mainly focusing, alright, on this region over here, those that's between 0 and 1.8. So for now, can you suggest if the following bonds they are polar or non-polar? This is more or less a recap from what we have learned previously. So for the first one, it's a FF bond, no? Non-polar, right? Because the electrons will be shared approximately equally between the two, since they are the same. Then second one? Polar, right? That's because the electronegativity difference of carbon is 2.5, fluorine is about 4.0, so the difference is 1.5, which makes it polar. So remember last time I mentioned that for polar bonds, right, what should you do to indicate that the bond is polar?
Move towards the non-electronic.
I mentioned that you have to draw the delta plus on the carbon, on the atom which receives less electron, delta minus on the atom which receives more electrons, and then you have to draw an arrow. Correct?
Yes.
So this is the correct way of depicting a polar bond. What about CH bond? None. That's because the electronegativity difference between carbon and hydrogen, if you calculate, is only 0.3. What about OH? OH will be polar, which means you should draw it in this way. Right? O is the negative one, hydrogen is the positive one, and then draw an arrow from the positive to a negative. And then lastly, C11O, it will be polar as well. So polarity doesn't depend on how many bonds there are, single, double, triple, or even quadruple bond. It only relies on electronegativity difference. So same thing, we can draw the delta minus and delta plus in this way. Alright? So next part, covalent bond formation. So previously we talked about ionic bond formation, metallic bond formation. Now let's look at covalent bond formation. So before that, you have to know that covalent bonds generally occurs in compounds that are formed between two non-metals. Do you know why? Why isn't it formed between a metal and a non-metal?
It will form an ionic bond because the electronegativity difference is more often larger than 1.8.
Yes, it's once again due to electronegativity difference. So usually between a metal and non-metal, the electronegativity difference is usually more than 1.8. So that's why you will interact via ionic bonding instead of covalent bonding. So in covalent bonding, what happens is that the atoms of both elements will join together and share their electrons. So they can share up to 3 electrons for a syllabus. But of course, you can share more, right, in real life. But you have to know these 3 only. So if let's say you have a hydrogen which has got 1 electron and another hydrogen which has 1 electron, we know that atoms will be stable if let's say they achieve the noble gas configuration, which means either 2 or 8 electrons in their valence shell. So these two can in fact share electrons to form hydrogen gas, which is H2. And in this way, each hydrogen will have 2 electrons. The same goes for oxygen, which can share 2 electrons, nitrogen, which shares 3 electrons. Alright? So we usually use dot and cross diagrams to depict covalent bonding, whereas where only the valence electrons are shown. Alright, so for dot and cross, we know that oxygen, we only show the valence electrons, we don't draw all the electrons. Same goes for nitrogen, we don't draw all the electrons. So these are known as dot and cross diagrams. And then another diagram that we usually use to draw is actually known as Lewis structure. Lewis structure is actually the simplified one because we just have to replace 2 electrons with a line. So those electrons that are being shared, they are known as bond pair because they are involved in a bond. Those electrons that are not involved in a bond, they are called lone pair. So take note that they are known as pair because they always come in twos. Alright. So for most of the time, more than two atoms can be joined together, and these are known as polyatomic molecules. So for example, for H2O, one oxygen can interact with two hydrogen on both sides to give you this structure. Same goes for carbon dioxide and methane, right, which can share up to all of these electrons. So the next type of covalent bond is known as a dative bond. So now if you consider the reaction between ammonia and H+, you have learned that ammonia is a base, alright, or alkali. H+ is an acid. So if you react these two together, what will happen? If you look at it at the structural level, alright, this is the structure of ammonia. So how many electrons are there around the central nitrogen? There are 8, right? Correct. So is it happy?
Yes.
It is happy. Then what about this hydrogen? How many electrons does it have?
0.
Hydrogen plus
0.
0, right? So is it happy?
No.
It is not happy. Then how does NH4 form then? So how NH4 is formed is when these two lone pair, these lone pair, both of them, which comes from nitrogen, they are being shared with this hydrogen, so as to form this kind of structure. So this is kind of different compared to the traditional covalent bond, because for traditional covalent bond, you need one electron from each, right, at least. But for this case, both of them, which is shared, comes from nitrogen. So for this kind of interaction is actually known as dative bond, where both of the electrons come from one atom. So now, if it interacts with hydrogen via this way, how many electrons are there around nitrogen? Still 8, right? So it's happy. Then how many electrons are there around this hydrogen? 2. So now it is happy as well. In other words, when you go from here to here, nitrogen is equally happy, but hydrogen becomes happier, which is the driving force for such a reaction. Alright? So how do you represent dative bond? For dot and cross, no problem. Both of them are being shared with hydrogen. But for the Lewis structure, we usually use an arrow to represent. The arrow doesn't mean it donates both of those electrons. It means that both of the electrons come from nitrogen. This is how we represent it. Any questions on this? Okay, right? I hope it's understandable. So these kind of bonds, they are known as dative bonds, and sometimes they are known as coordinate bonds. Alright, it's just how they are named. So one more thing to take note is that although dative bonds, they are represented differently from normal covalent bonds, they have identical chemical and physical properties. Now, what do I mean by identical chemical and physical properties? If you look at the structure of NH4+, right, which is this one over here, we can see that this nitrogen-hydrogen bond is a normal kind of covalent bond, whereas this one is a dative bond. So, what these sentences ultimately mean is that this bond and this bond, there's no difference. You cannot differentiate it. It's just the way they represent it. Alright, or rather it's just a name that you call it. So they are identical. Alright, you cannot differentiate them. So next will be the drawing of dot and cross diagram. This part is the part whereby most students have problem with. So therefore I've derived a few steps for you. So if you were to follow these steps, generally you should get the correct answer. Alright, unless there are some exceptional cases which I cannot foresee, yes. So don't worry about these steps, I'll go through with you. For now, you just have to fill in the blanks. Alright? Alright, you just have to fill in the blanks as of now. Later on when we are practicing, we'll go through this step by step. Alright, so after you fill this in, let's look at, let me just briefly go through. So what are the general steps? I might as well just use the example over here. Right? For example, if let's say the question asks you to draw ammonia NH3. So the first step they should do is to place the atom of the least number in the center and the rest of the terminal atoms symmetrically around it. So what is the atom of the least number here? Evan? What's the atom of the least number here? Nitrogen, right? Nitrogen only have 1, hydrogen have 3. So first you place nitrogen in the center, and then the rest of the terminal atoms symmetrically around. So if you have 3 hydrogens, how do you place it symmetrically? Basically, one each corner, correct? So first step done. Next step, distribute valence electrons of the central atom evenly, representing each electron as a cross or a dot. So for this case, I'll distribute it evenly as a cross or a dot. So for this case, I'll let it be a dot. And then next, what I do is that I'll distribute valence electrons of each terminal atom such that each atom donates 1 electron to pair up with the central atom. So I know that hydrogen contains 1 other electron, so you'll pair up with the central nitrogen in this way. Alright? And then next, I'll distribute the remaining valence electrons as lone pair around the atom. I know that nitrogen is from group 5. I already used up 3 electrons, it's left with 2. So therefore, I draw the 2 electrons on this nitrogen to act as a lone pair. Once again, for this lone pair, I don't draw like that. Drawing like that is wrong. This is wrong. Why? Because electron always comes in a pair. So therefore, I should always draw them together. It doesn't matter where you draw it, as long as they are together. So next, step 4. If terminal atoms still do not have an octet, form multiple bonds or form dative bonds. For this case, I've achieved the noble gas configuration, so I can skip step 4. Step 5 is ions are involved. I don't have ions. So basically, this is the final structure of ammonia. So if I want to draw the Lewis structure, I just have to translate the shared electrons to a single line. And then for the lone pair, I just leave it on nitrogen. And this will be the Lewis structure of ammonia. So these are the general steps. Later on, you'll try it. So next, what is valency? Alright. So if you look at valency over here, valency of an element is the number of electrons an atom will gain or lose to achieve the noble gas configuration. Alright. For example, for hydrogen, its valency we will say that it is 1. Alright, you will gain 1 electron to achieve the noble gas configuration. Whereas for boron, it is from group 3. Alright. So its valency will be 3, carbon is 4, nitrogen is back to 3. Why nitrogen is 3? Because nitrogen is a group 5, you need to gain 3 more electrons. So therefore its valence is 3, followed by 2, followed by 1, and for noble gas is 0 because they don't have to gain or lose any electrons. And take note of the naming for group. For group, you can either name it in Arabic numerals 13, 14, 15, 16, 17, 18, or in Roman numerals 3, 4, 5, 6. Please don't do vice versa. You get it wrong. So what does the above imply, and how does it help you in your dot and cross diagram? The above implies that for a particular atom with a valency of n, you tend to form n bonds to achieve the noble gas configuration. For example, hydrogen, the valency is 1, right? So you tend to form 1 bond. Carbon, the valency is 4, you tend to form 4 bonds. Carbon, same thing goes here. Even though it's a triple bond, it's considered as 1, 2, 3, 4 bonds. Hydrogen is 1, and so on. And for nitrogen, here you can see that it forms 3 bonds, excluding this, which is according to the valency. Same goes for oxygen. Alright? And there are some shortcuts for oxygen. So for oxygen, there can only be 4 circumstances. One of them is this oxygen, alright, is joined via 2 bonds on either ends to form this kind of configuration. That's the first possibility. The second possibility is that if let's say it's an oxo ion, this will be its structure. Alright. Now, this is usually for n-ionic molecules containing oxygen. What do I mean by this? For example, CO3 2 minus, NO3 minus. For these kind of molecules, these are known as oxo anions. Oxo means oxygen containing anions. So for example, if I ask you to draw the structure of CO3 2 minus, what will it be? What's the first step?
Oxygen, draw C.
No, C in the middle.
C in the middle, right? And then I distribute oxygen
around it.
So what's the next step?
Fill in the electrons.
Fill in the electrons of carbon. So carbon here. Think about oxygen. We just pair up one with carbon first. So now each of these oxygen will be left with how many electrons to play with? 6, right? Sorry, 5, right? Because we already used 1. So same goes for this. Same goes for this.
But carbon still.
Now, is this oxygen happy?
No.
Are all the oxygen happy? No, right?
No.
The oxygens only have 7 electrons. The carbon at the central only have 6 electrons. So what do you think we should do? What's the next step?
Share one to another.
We will have to form multiple bonds, right? This is step number 4. So for example, we take the top oxygen as an example. If we were to share another electron with carbon, now this oxygen will be happy. Correct? Because we already have 8 electrons. Is this carbon happy?
Yeah.
Carbon is happy, right? But are these 2 oxygens happy?
No.
Can I form more bonds with carbon? No, right?
No.
The central carbon will be too happy. So what should we do? Remember, we still have the 2 minus. And based on this rule, what we know is that the additional electron, or rather the additional 2 electrons, one of it should go to this oxygen, alright, and then another one should go to this oxygen, which makes it happy. So in other words, the Lewis structure, alright, will be something like this. This means that one negative charge on this oxygen and another negative charge on this oxygen. We can either draw it this way or this way. Alright? So this is what's meant by this rule over here. But for your school, I believe they want you to draw this way. Alright? So please just follow this way. So this is why such a shortcut is useful. Because as long as it contains oxygen and is aniconically charged, most of the time the anion, or rather the electron gained, goes to oxygen. So the next possibility is that there's a dative bond to oxygen. But for this is for information. But that doesn't mean they cannot ask. So what's one example of this? This will be NO3 minus. So by the same logic, we will place N at the center, the 3 oxygen at the terminal end. Alright? So each of these nitrogen will share 1 electron with this oxygen, and this oxygen will in turn share 1 electron with nitrogen. Alright? What time did you sleep last night?
Quite late.
How late is late?
No.
12, you call that late? I slept at 1:30, you know.
I slept at 1 because I wake up early.
So this is the structure of nitrogen, of NO3.
I need some tea.
So take note. You need some pee? What?
I conveniently already finished all my diary, so not
Now this part is very important. It determines whether you can get a mark or not. Alright. So same thing, this is what we did as per CO3 2 minus, right? Quite similar.
Yes.
But then remember what's the shortcut that I told you? If it's an oxo anion, if let's say you have -1 charge, you have -1, you have 1 type of this bond.
Yes.
If it's -2, that means you have 2 types of this.
Yes.
So for this case, how many types of this do you have? 1, right? In other words, that additional electron must go to this oxygen. Right? Then, how does this interact with nitrogen and this interact with nitrogen?
Nitrogen still has 2 more.
So remember, nitrogen still have 2 more electrons, right, to play with. So I can in fact form 1 more bond with this oxygen. Alright? But then I'll be left with 1 more electron for this nitrogen.
Yes.
Can this electron pair up with this one?
No.
Why? That's because nitrogen have more than 8 electrons, right?
And
Which
become too
is not
happy.
possible. It'll be too happy. So what can I do with this additional electron then? I cannot interact with this because we already settled this. You already got 8 electrons. I cannot touch these because we already have 8 electrons. But then I have additional 1 electron which I cannot get rid of.
Dative
So
bond.
instead of sharing it, why not both of them I share it with this oxygen? Correct? By doing it this way, this nitrogen will retain its octet configuration
Yeah. Being too happy.
without sacrificing this oxygen having less than 8 electrons. Alright? So that's why for this case, the structure of NO3 minus will be, the Lewis structure will be like this.
And then a dative bond.
With a minus outside. Alright? You can either draw the minus outside or allocate this minus to this oxygen. And the next one, double bond to oxygen. So we're already seen quite a lot of double bonds.
Yeah.
So if all these three doesn't work for oxygen, the last option must be a double bond to oxygen. Like what we did for CO3 2 minus and NO3 minus. Alright? So these are the only 4 possibilities. So the general rule of thumb, very important. Alright, recorded as evidence. If this doesn't work, go to this. If this doesn't work, go to this. If this still doesn't work, don't have to try. It's definitely the last one. So this should be the order that you should think about. Don't skip any. Alright? So now, all these are some practice questions. I guess this will keep you occupied until the end of today's lesson. So please draw the dot and cross or Lewis structure for the following molecules. Alright? Yeah, sure. Do the easy ones as example, and then you can do the harder ones. So for first one, Cl2, basically there's only one way that you can connect, right?
Because we are recording two balls.
There's only one way that you can connect. Alright?
You never record this,
Huh?
This one never get recorded.
Recorder is already continuing.
Oh.
Yeah. So this is the only structure that, yeah, the screen and my voice.
Oh. Our voice as well.
And your voice.
Oh.
So this is the structure of Cl2, alright? For this part, we'll do it next time, suggesting a number of sigma and pi bonds because we haven't learned it yet. So this is the structure of Cl2, then HCl, same thing, pretty much. You can only have one structure. Alright, this is HCl. For CH4, same thing. If you don't know, we can start with the center. And then we draw 4. I already covered these just now. Next one, CO2. C being the least number, I will place in the center. The O will be at either ends, evenly distributed. And then in order to achieve octet configuration for both the central and terminal ones, alright, I will have to have this kind of structure whereby carbon is double bonded to oxygen on this end and to the other end. Alright? So just to do more, alright, HCN. So for this, the tip is given is that C is the central atom. So H must be on the left, the other N must be on the right. So H having a valency of 1 will be connected to this carbon. Carbon having a valency of 3 will be connected to nitrogen. And remember to draw a lone pair. Any structure without a lone pair you will be awarded with 0 marks. Alright? The next is oxide ion. So what's the trick? Remember, I mentioned that whenever you have an oxo anion, it's usually oxygen which have the negative charge. In other words, this oxygen should be the one which gains that additional electron. So this will be how we draw it. Alright? We'll put a negative charge outside to show that the anion is negative charge. Or another way that you can draw it, depending on your school, is that you draw it this way. Alright? But I prefer this way. Next one, nitrite ion, NO2 minus. So same thing, I place nitrogen at the center, the 2 oxygen at the end. So how do you connect these two together? Take note that it is once again an oxo anion, right? So for oxo anion, you know that one of the oxygen must have that additional electron, and it must be bonded this way to nitrogen. Then how does this nitrogen interact with this oxygen then? We know that nitrogen is from group 5. After we used up 1 electron, it still have 4 electrons. So logically speaking, 2 of it must be shared with this oxygen, and then the other 2 becomes the lone pair. So this is the structure of nitrite ion. So this nitrogen at the center has a lone pair. And also don't forget the lone pair on this oxygen. So we have to draw everything. Alright, now what about nitronium ion? For this nitronium, is it considered as oxo anion? No, because it's a cation ion. So in this case, the question is, so which atom in NO2 loses the electron? If you look at the steps that I mentioned previously, especially step number 5, I mentioned that for anions, electrons is usually added to a more electronegative atom, which makes sense if you think about this case, because usually oxygen, which is the second most electronegative atom in the whole periodic table, we usually gain that negative charge. So for this case, if we compare nitrogen versus oxygen, nitrogen is actually less electronegative based on the trend in the period table. So what this means that the electron will tend to be removed from nitrogen instead of oxygen. Alright? So therefore, with this in mind, alright, we can start off by drawing this. And we know that nitrogen, upon losing one electron, only have 4 electrons. So just nice for it to form a double bond on the left and a double bond on the right. Alright? Because it lost that 1 electron. 5 minus 1 give you 4. So for the left over 4 electrons, 2 will be shared with this oxygen, 2 will be shared with this oxygen to achieve this structure over here. And don't forget the positive charge. So you can either draw it this way or draw it this way. Alright? This way will be clearer in saying that, oh, the electron loss actually comes from nitrogen. But for this case, it's slightly more vague because it doesn't exactly tell you which electron, which atom the electron is being lost exactly. Alright? For this nitrate, just now I already drawn it. Alright, I already show you how to draw it. This is the structure of nitrate. But remember to draw the lone pairs. Any structure without the lone pair will be wrong. And a square bracket outside minus. CO32 minus already shown you as well. How to draw it just now. Same thing, draw all the lone pairs. Next, what about PCl4 plus? You try to draw it, alright? So our PCl plus, the electron loss comes from which atom? Because P is less electronegative, right? You don't really have to refer to the electronegativity table. You can recall based on the trend. It increases this direction and up the table. So you can easily predict which one is higher. So you have PCl4. Remember to draw the lone pairs. COCl2. If I tell you C is the central atom, you know C must be double bonded to O, connected to Cl, connected to Cl, alright? Same thing, just draw a lone pair. Next one, CO, carbon monoxide. You all know what is carbon monoxide? Sorry, there's no bracket. Carbon monoxide is a toxic gas. Alright, it's odorless. It's odorless and it's tasteless.
It's the one that kills the minds.
Yes.
Is that the minds? Right?
So you'll die a slow death, basically. So if you breathe in carbon monoxide, basically you won't feel anything, and you just slowly fall into a deep sleep, and then you'll die. Alright.
That's how my.
You'll bind irreversibly to your hemoglobin in your blood, and inhibits your red blood cells' ability to carry oxygen around your body, and basically you'll suffocate to death before you even know it.
It's the most famous way to die, to be honest.
Alright.
How do you know?
How do I know? Oh.
Because literally.
Come, draw the structure of CO. We'll end after this page. And the rest, alright, you can go back and practice. I suggest you to draw the dot and cross of carbon monoxide first, before you draw the Lewis structure. Right, it will be
much
easier. I'll draw it. You know carbon monoxide definitely exists, right? But how come its structure is so difficult even though there are only 2 atoms? This is the most
Cancer.
easiest looking question, but it's the most difficult question of an exam. Alright. So how do you draw this? Basically, I believe now you're at the stage of something like that, right? And then you have 2 electrons on this carbon, and then you have 6 electrons. You have 4 more electrons left on oxygen. So once you are at this stage, that's good enough already. Now the question is, how do you further interact with them? Because this carbon, it doesn't have 8 electrons, right? Although this oxygen has got 8 electrons. Alright? So how are you going to interact with it? Basically, remember this oxygen, it still has 2 electrons over here. So what it can do is that it can share both of these electrons with carbon, right? So once you do this carbon have 8 electrons. This oxygen has got 8 electrons. Correct? In other words, for the bond between carbon and oxygen, 2 of them are normal covalent bond, 1 of it is a dative bond. So how do we illustrate it? We illustrate it this way. Alright? So nothing wrong, right? Previously I already mentioned that a dative bond is just like a normal covalent bond. Correct? So this is the structure of CO. And then last one is Cl2O. So atom of the least number is oxygen, and you have chlorine on either side. So this one is quite straightforward. But remember to draw in the lone pairs. Alright?